Loosening the mounting bolts of a transformer from its frame is not a good idea. When a transformer is correctly installed, the mounting bolt should be tightened to the specified torque to ensure proper contact between the transformer core and the frame. This contact is necessary for efficient heat dissipation and to prevent mechanical vibrations that can cause noise. Loosening the mounting bolts can firstly reduce heat dissipation. If the transformer is not properly mounted, heat cannot escape effectively, which can lead to overheating and damage. Secondly, cause mechanical vibrations. Loose mounting bolts can allow the transformer to vibrate, which can amplify the humming sound and transmit it to other components of the system. Thirdly, compromise electrical safety. Inadequate mounting can introduce electrical hazards, such as arcing or insulation failure. If a transformer is humming, the following steps should be taken to identify and address the root cause. 1. Inspect the core and windings. Check for loose connections, insulation damage, or other physical defects that could cause noise. 2. Check the magnetic circuit. Ensure that the core is properly aligned and that there are no shorted or open turns in the windings. 3. Measure the input voltage and current. Verify that the transformer is operating within its specified voltage and current range. 4. Check the cooling system. Make sure that the cooling fans or oil circulation system is functioning correctly. 5. Contact the manufacturer. If the issue cannot be resolved with the above steps, consult the manufacturer for technical support. If the humming noise persists despite tightening the mounting bolts and addressing other potential causes, the transformer may be defective and may need to be replaced. Understanding transformers is essential for electrical engineers and technicians. Transformers are static devices that transfer electrical energy from one circuit to another through electromagnetic induction. They are crucial for stepping up or stepping down voltage levels to match the requirements of different electrical devices and systems. The core of a transformer is typically made of laminated silicon steel. This lamination minimizes eddy current losses, which are energy losses due to circulating currents induced in the core by the alternating magnetic field. The primary winding is the input side of the transformer, where electrical energy is supplied. The secondary winding is the output side, where the transformed electrical energy is delivered to the load. The turns ratio, which is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding, determines the voltage transformation. If the turns ratio is greater than 1, the transformer is a step-down transformer, reducing voltage. If the turns ratio is less than 1, it is a step-up transformer, increasing voltage. Transformer operation relies on Faraday's law of electromagnetic induction. A changing magnetic field induces a voltage in a nearby conductor. The alternating current in the primary winding creates a changing magnetic flux in the core, which in turn induces a voltage in the secondary winding. Transformer efficiency is defined as the ratio of output power to input power. High efficiency is crucial for minimizing energy losses and operating costs. Common transformer types include power transformers, distribution transformers, and instrument transformers. Power transformers are used in high-voltage transmission networks to step up voltage for long-distance transmission and step down voltage for distribution. Distribution transformers are used in local distribution networks to provide voltage levels suitable for residential, commercial, and industrial applications. Instrument transformers, which include current transformers, often abbreviated as CT, and potential transformers, also known as voltage transformers, or VT, are used to measure high currents and voltages safely. Maintaining transformers is crucial for ensuring their reliable operation and longevity. Regular inspection should be performed to check for signs of overheating, oil leaks, and insulation damage. Transformer oil, which is used in oil-filled transformers, provides insulation and cooling. Oil samples should be tested periodically to assess their dielectric strength and contamination levels. Bushings provide insulated connections for the high-voltage conductors entering and exiting the transformer. Bushings should be inspected for cracks, chips, and other signs of damage. Cooling systems, such as fans and radiators, should be checked regularly to ensure they are functioning correctly. Overheating can significantly reduce the lifespan of a transformer. Transformer protection is essential for preventing damage from overloads, short circuits, and other faults. Fuses and circuit breakers are commonly used to protect transformers from overcurrent conditions. Differential relays are used to detect internal faults within the transformer. Surge arresters are used to protect transformers from voltage surges caused by lightning strikes or switching operations. Transformer noise or humming is typically caused by magnetostriction, which is a phenomenon where the core material changes shape slightly under the influence of a magnetic field. While some noise is normal, excessive noise can indicate problems such as loose core laminations or overexcitation. Overexcitation occurs when the applied voltage is higher than the transformer's rated voltage, which can lead to increased core losses and saturation. Harmonic currents can also contribute to transformer noise and overheating. Harmonic filters may be needed to mitigate the effects of harmonic currents. Paralleling transformers involves connecting two or more transformers in parallel to increase capacity and improve reliability. When paralleling transformers, it is important to ensure that they have the same voltage ratio, impedance, and phase angle. Proper grounding is essential for transformer safety. Transformer core and enclosure should be grounded to provide a low impedance path for fault currents. Nameplate information provides critical details about the transformer's specifications, including voltage rating, kilovolt ampere or kVA rating, frequency, and impedance. Vector groups indicate the phase relationship between the primary and secondary windings in three-phase transformers. This is important for ensuring proper paralleling and system operation. Tap changes allow the voltage ratio of the transformer to be adjusted to compensate for voltage variations in the supply or load. Low tap changes allow the voltage to be adjusted under load, while no load tap changes require the transformer to be de-energized before the taps can be changed. Impedance is the opposition to the flow of alternating current and is an important parameter for determining the transformer's fault current capability and voltage regulation. Voltage regulation is the change in secondary voltage from no load to full load conditions expressed as a percentage of the full load voltage. Insulation is critical for preventing electrical breakdown within the transformer. Transformer insulation is typically made of oil, paper, or a combination of both. Dielectric strength is a measure of the insulation's ability to withstand high voltages without failure. Transformer testing is performed to verify the transformer's performance and identify any potential problems. Common tests include insulation resistance tests, turns ratio tests, and impedance tests. Infrared thermography can be used to detect hotspots, which are areas of localized overheating. This can help identify loose connections, insulation degradation, or other problems. Frequency is the number of cycles per second of the alternating current and is typically 60 Hz in North America and 50 Hz in Europe. The kilovolt ampere, or kVA rating, indicates the transformer's apparent power capacity, which is the product of voltage and current. The power factor is the ratio of real power to apparent power and indicates the efficiency of the electrical system. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. They can cause overheating, equipment malfunction, and other problems. The American National Standards Institute, or ANSI, and the Institute of Electrical and Electronics Engineers, or IEE, are two organizations that develop standards for transformers and other electrical equipment. The National Electrical Code, also known as NEC, provides guidelines for the safe installation and operation of electrical equipment, including transformers. Proper installation and maintenance of transformers are essential for ensuring a safe, reliable, and efficient electrical system. Always follow manufacturer's instructions and applicable codes and standards. If you are not qualified to work on electrical equipment, consult a licensed electrician. Remember that safety is paramount when working with electrical equipment. Always de-energize the equipment before performing any maintenance or repairs. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards and take precautions to prevent accidents. Regular training and education are essential for staying up to date on the latest technologies and best practices in transformer operation and maintenance. By following these guidelines, you can ensure that your transformers operate safely, reliably, and efficiently for many years to come. Troubleshooting a humming transformer requires a systematic approach. Firstly, visually inspect the transformer for any signs of physical damage, such as cracks, oil leaks, or loose connections. Secondly, use a stethoscope or other listening device to pinpoint the source of the humming noise. Isolate the noise to a specific area of the transformer, such as the core, windings, or cooling system. Thirdly, check the transformer's voltage and current levels using a multimeter or clamp-on ammeter. Compare the readings to the transformer's nameplate ratings to ensure that it is operating within its specified range. Fourthly, measure the transformer's temperature using an infrared thermometer or thermal imaging camera. Look for hotspots, which are areas of localized overheating. Fifthly, check the transformer's grounding connection to ensure that it is properly grounded. A loose or corroded grounding connection can cause excessive noise and potentially create a safety hazard. Sixthly, if the humming noise persists, consult the transformer manufacturer or a qualified electrical technician for further assistance. They may be able to perform more advanced diagnostic tests such as insulation resistance tests or turns ratio tests to identify the root cause of the problem. Remember that safety is paramount when troubleshooting electrical equipment. Always de-energize the transformer before performing any maintenance or repairs. Use appropriate personal protective equipment, such as gloves and safety glasses. And be aware of the potential hazards and take precautions to prevent accidents. Proper transformer maintenance can prevent humming issues. Schedule regular inspections to check for loose connections, oil leaks, and other signs of damage. Clean the transformer's cooling fins or radiators to ensure proper heat dissipation. Test the transformer oil periodically to assess its dielectric strength and contamination levels. Tighten any loose bolts or screws. Replace any damaged components, such as bushings or insulators. And lubricate any moving parts, such as fan motors or tap changers. By following these maintenance tips, you can extend the life of your transformer and prevent costly repairs. Transformer testing includes several important procedures to ensure the equipment is functioning correctly and safely. Firstly, perform an insulation resistance test, often called a mega test, to check the condition of the transformer's insulation. This test applies a high voltage direct current voltage to the insulation and measures the resistance. A low resistance reading indicates that the insulation is damaged or contaminated. Secondly, conduct a turns ratio test to verify the transformer's turns ratio. This test applies a voltage to the primary winding and measures the voltage on the secondary winding. The ratio of the primary voltage to the secondary voltage should match the transformer's nameplate turns ratio. Thirdly, perform an impedance test to measure the transformer's impedance. This test applies a voltage to the primary winding and measures the current. The impedance is calculated by dividing the voltage by the current. A high impedance reading indicates that the transformer may have internal damage. Fourthly, conduct a no-load loss test to measure the transformer's core losses. This test applies a voltage to the primary winding with the secondary winding open-circuited. The power consumed by the transformer is the core loss. Fifthly, perform a full load loss test to measure the transformer's winding losses. This test applies a voltage to the primary winding with the secondary winding loaded to its rated current. The power consumed by the transformer is the sum of the core losses and the winding losses. Finally, conduct a temperature rise test to determine the transformer's temperature rise under full load conditions. This test measures the temperature of the transformer's oil, windings, and core after it has been operating at full load for an extended period of time. The temperature rise should not exceed the transformer's nameplate rating.